I'm going to use the audio read function to read the film that I have created already. Now I'm going to use the sound function to run my voice. This is Jia Zheng. Before I go, we need to change the IP from a double to a single column. Now I'm going to create a time vector. It's from 0 to the length IP minus 1, then divided by fs, then plot t against the IP, then label the y-axis as amplitude. Then label the x-axis as the time seconds. Then run it. Then we can see the y-axis is amplitude and the x-axis is time seconds. The code here and run it, and now we get the tone frequency is 2481 and the noise cutoff frequency is 16,929. Now we need to create a random signal. It's the same size as IP. That's random. The same size as IP. Yeah, high frequency noise. So the NS will be the broadband noise. So we are going to use the Butterworth function, and we make a sixth order and set the cutoff frequency to be noise cutoff frequency. And here 16929, then divided by fs divided by 2. So that's our normalized frequency, and we need a high frequency, high pass filter to create the high frequency noise. Now use the filter function as equal filter b comma a comma s. That's going to store it by 2 in that variable ns. Now then we created a tone equal to 0.1 time cos time 2 time pi time the frequency, 2 pi frequency, and here tone frequency 2481, then time the time t. Yeah, so we can get the tone, and we can see tone is a row vector and the ns is a column vector. Then we created the speech signals, that is signal equal the new speech signal is original signal plus the noise, the high frequency noise is NS, and then plus the tone. Yeah, we decided because the tone is a row vector, so we use a tick. Yeah. We need to use the butter function again. So we set a second order function filter, and then the filter has to be half the color frequency. So that is 16929 divided by 2. So and then we do the same thing with before, fs divided by 2. Yeah. So that's a low pass filter. We're going to draw a signal flow diagram. So the B coefficient is this, A is this. Now we are going to draw a signal flow diagram. So xn is input, multiply this one 0.1937 to the yn output. Next, delay, multiply here 0.3874, delay, multiply here 0.1937, same thing to output yn, delay, multiply here. We need to change to positive. So 0.4297, delay, multiply, that's minus 0.2044. So the difference equation is yn equal 0.1937 xn plus 0.3874 x minus 1 plus 0.1937 x minus 2 n minus 2, then plus 0.4297 sorry, that's y n minus 1 minus 0.2044 y n minus 2. That's the difference equation. That's the diagram. The first 3 input is this 0.097, 0.0956, 0.0727. So the xn, we get the output, the first 3 inputs of the system. So xn equal 0.0997, 0.0956, 0.0727. That's the x0, that's x1, that's x2. So the y0 equal 0.1937 multiplied 0.0997. and here this xn minus 1 0 all 0 all 0, so yn just equal these two numbers multiply. So we calculate use MATLAB. 0.1937 multiply 0.0997. The answer is 0.193. We get from MATLAB is 0.0193. Then we calculated the y1 equals 0.1937 multiply x1 plus 0.3874 x0. This one is 0, so we pass it, plus 0.4297 y0. So the value is, this one is still 0, so we pass it. So that's 0.1937 multiply x1 here 0.0956 plus 0.3874 multiply x0 here 0.0997 plus 0.4297 multiply y0 we have calculated here, so that's 0.0193. So we calculate use MATLAB. We calculate use y1. So now we calculate y1 use MATLAB. It's 0.1937 multiply 0.0956 plus 0.3874 multiply 0.0997 plus 0.4297 multiply 0.0193. So we get y1 is 0.0654. Now we get the value for y1 from MATLAB is 0.0654. So we continue to calculate y2 is equal 0.1937 x2 plus 0.3874 times x1 plus 0.1937 x0 plus 0.4297 y1 minus 0.2044 y0. So now we just 0.1937 multiply x2 and here is 0.0727 plus 0.3874 times x1 and here is 0.0956 plus 0.1937 x0 here is multiply 0.0997 plus 0.4297 times y1 and here is multiply 0.0654 and minus 0.2044 times y0 and here is multiply 0.0193. So we continue using MATLAB to calculate y2 is 0.193 937 multiply 0.0727 plus 0.3874 multiply 0.0956 plus 0.1937 multiply 0.0997 plus 0.4297 multiply 0.0654 minus 0.2044 times 0.093 so we got y3 is 0.0946. Now we get value from MATLAB for y2 is 0.0946. So now we are going to check our calculation is correct. Sig 3. So that's what we should get. First value, we just see that is same for the that's the y2 is same, and for y1 is this one is still same. So the for y0 y0 I here 0.0193, this is y0, so 0.0193, so we get all calculation is correct. To design a minimal order filter, so n omega equals we use the bottled, and we give the pass band frequency width is the 0.5, and the stop band frequency is the noise cutoff frequency. So and here is 16929, and divided by fs over 2, then give it the pass band ripper, which is 3 dB. So and that's 3, and the stop band attenuation is 60 dB. So we got equation, so right, and then we get the n and omega. Omega, and let's give the order and the frequency. Then we use the border function. That's b again, a equal border n omega. Okay, now that's the design the filter. To design a second filter, we will use the difference coefficients. So we use the b1 a1 equal to border. So that's we can do a high order filter. We can set it is 4, then the cutoff frequency we can use the tone frequency is 2481, yeah, minus 50. That mean is come back 50 hertz. Then we can 2481 plus 50. So this is mean the code is mean is this is going to filter all the region of 100 hertz in total. So then we need to do the same thing with before divided by fs over 2, and that's become to normalize the frequency. So the next step is we need a stop band filter. So we type in stop. Okay. Yeah, it's work. So that's the second filter design. We need to make sure if it's stable, we can use zipline. The code V1, A1 to check it. So we can see here. That's stable. That's inside the circle. Now we are going to track the attenuated frequencies by at least 60 dB. So we use the tone frequency is 2481 divided by fs over 2. We get that's normalized frequency. So the answer is 0.1125. So we want to make sure this frequency is attenuated by at least 40 dB. So we use phrase z function and b1 a1 coefficient, and we still need to put a third parameter that will be make the filter a little bit smoother. So we can put 10,000 and right. Then now we can see the diagram picture, and we just put a bigger, I think here, okay. So now our frequency of 0.1125 which would be there. Yeah, and so we can see that frequency are reduced quite a bit by at least 80 dB. So that frequency work. Now let's filter the signal. So y equal filter b a and sig. This is to the first filter. So we are going to take the output of the filter. So which the y and filter it into the input of the next filter. So that's b1, a1, and y. So we'll just put y into this system, and we are filling y and storing in y1. Now we are going to plot the magnitude frequency of the content of the input in hertz. So let's create a frequency axis. So f(x) equal it's from 0 to the length of the input to IP, and -1 because all the variables IP, they're all going to be all the same length, then divided by length of IP. Multiply fs, and now that to get a frequency axis in hertz, then we're going to plot the frequency axis against the ABS FFT of SIG. So plot FES ABS FFT SIG. So that's the input. So run it. Now we can see that is a high frequency noise, that the tone and speech is down at there. So now we hold on and plot y1. So just y1. So now we can see the y1 is in the orange. Yeah, we can see here. Now it's being reduced. The orange won't be have any high frequency or the tone. So you can see here it's really clear. The last part is to label the axis. So the y label magnitude, and x label frequency in hertz. Yeah, here. I look at the frequency response of that signal. So freq that BA. So this is the first filter. You can see that this is the frequency response, and we are going to go for low frequency. So I look at for phase shift about 45 degrees. So now we found the 45 degrees. So let's create a tone of the frequency. So that's the x-axis 0.107 divide time fs over 2. Now we get the answer is actual frequency. So that's about 2360 hertz. So that frequency at least should have a phase shift. So the tone equals 2 pi 2359. Let me see, try 1, 2, 3. Okay, 0.3, and time t. So we bypass this signal true. So y equal filter b a and the tone. So then plot the tone. The plot tone. Now we get the tone, then hold on and plot y, the output. Because the online MATLAB without function with horizontal zoom, so I tune to my laptop. So now I plot the tone and the plot y. So now horizontal zoom in. Okay, now we can easily to see that. So how to see that? We can just calculate percentage of the wavelength by doing 360 divided by 45, and the answer is 8. So that's 1/8 of waveforms. So we can see that just 1/8. Yeah, that's the 45 degrees the phase shift. Yeah, that's correct. Last step is to do some explanation for each element. And for the first one, just record my voice and just import the audio signal into the MATLAB and run it, and we will listen our voice. And for second one is just story and sampling frequency. Use the record always audio signal into a variable fs. That's second one. For the third one, just plot the speed signal in the time domain, again the time in second, and don't forget the label axis. So for the fourth part, so run the code from the video checklist and add here, and then just we will get the tone frequency and noise cutoff frequency. That's for fourth part. For the fifth part is synthesis the high frequency noise and the tone and this to the speech signal. That's what we done on the video. That's just put the equation and add all the signal together. And for the sixth part is design second filter. Just use the buffer function again, and the frequency is cutoff frequency set equal to the half one. Half is important to the noise cutoff frequency. For the seventh, we need to draw a signal flow diagram. And because we get B coefficient and A coefficient, so we can draw the signal flow diagram and just write out the difference equation. And yeah, that's for the seventh step. For the eighth step, and then we calculate just by hand the first three outputs of the signal. Yeah, we have calculated. And for the ninth, filter out the combined signal, use MATLAB filter function, and track that the first three outputs match our hand calculation. We just use the simple function to filter function to track the output with our calculation by hand results if they are same or no same. We get same value, so all the calculation is correct. So for the 10th step is design a minimal order filter. The important is reduce the high frequency noise at least 60 dB with the maximum of 3 dB ripple along in the passband, and the passband is 0 Hertz to fs over 4 Hertz. That's just the design a minimal order filter. Just put value at following. Yeah. And for the 11th, so we just design a second filter, use the MATLAB function again, just the value is following. And this part we need to track it. If it's stable, we can track the pose and zero if they are in the circle or out of the circle. So we set fourth order, so they are in the circle, so the second filter is stable. So for the 12th step, we need to apply both the filter to the combined signal and plot magnitude frequency contents of the input and output in hertz. That's easy. We do it in the video. And then don't forget to label the axis, x-axis and y-axis. So for the 13th, identify a low frequency component that will be produce a significant phase shift in the first filter, at least pi over 4 readings. So we do that for 45 degrees. So and pass a sinusoidal of the frequency through the filter. So we get that, and we plot the Y filter and the tone, and we just track the phase shift if they are 45 degrees. We get the 45 degrees, so all correct. So this last part we done it, so our work is finished. Thank you so much for watching the video. This is a long video. Thank you so much.